years, almost 20 years ago, right? And there was also a department that's called physical intelligence. I guess that's 20 years ahead of everyone else. Right? I got it right?
In some sense, yes. But it was much more in the world of nanorobotics that this happened in this topic.
Okay. Okay, great. Some background of today's panel, why we have this panel at this time. I think we're at a very exciting time. A lot of progress is happening in robotics, and a lot more people are coming to the field. People are generally excited about it. I think through all this development, we're really trying to answer one of the deepest questions in AI. That's essentially, why can AI system be the world champion in Go, but cannot do the things a 3-year-old is able to do? With all these recent advancements in the field, robotic foundation models or these big models, I think we're partially answering this question by building a computational brain, which could, in principle, turn computation into physical capabilities, and which is very powerful, because if we solve it, then we could, in principle, actually fundamentally change the physical world with computation. I think, personally think this is a new big science, and as an AI scientist, this is really a golden age, a really exciting time for us to do research in this field. At the same time, we also see a trend that's really happening, is that the gap between fundamental research and impact for industrial products are really shortening. For example, Google's Gemini is basically fundamental research. But once it was built, and it could be launched the very next day and be used by billions of users in the world. So that's why we have today's panel, where we have a very diverse background of excellent researchers, founders from academia and industry. Some of the panel guests actually navigate their career paths between academia and the industry. So it's really great to have both of them actually on the stage. So I'll start to ask a few questions to a group, maybe a group of you, and then at the end, if we have a little bit of time, we'll take some questions from the audience. So the first question actually goes to Sergey and Stefan. I think both of you have been working on this field for a very, very long time. Stefan, you pretty much devoted your entire career in this field. You work on imitation learning, reinforcement learning, robotic locomotion manipulation, pretty much essentially every topic in machine learning and robotics, and in the past 30 years. And many of us actually grew up with your papers. Those are essentially seminal fundamental work before the deep learning wave actually really take off. Sergey, you started the very first robot farm in Google at 2016. That was 7 KUKA robot arms, if I remember correctly. And in fact, I learned this back then brand new topic, deep robotic learning, from your class in spring 2017, when I was still a graduate student at Berkeley. Peter, you are also a student there, right, too? The course number back then was CS 294-112. I still remember it. These days, actually, robot farms are not new at all. I mean, this year, China alone has 200 companies building those data collection facilities. So I think both of you were part of the effort creating and defining this field when it did not exist, nourish this field when it was small, and keep push the frontiers when everyone else realizes this is a big thing. So my question to you is that you have seen a lot of ups and downs, hypes during your career, in robotics and robot learning particularly. What do you think has fundamentally changed to push the field to where it is today? And how is this time different from the previous many hypes and peaks you have seen in the past during your career?
So should I start? I think I will start, and most likely Sergey will complete that. I think one thing you might have noticed today is all the robots you're seeing, they have cameras and they process vision, and they can process vision effectively. Now, this is actually not such a old and established component of robotics. I think the main breakthrough came essentially with a Microsoft Kinect sensor. This is now 20 years ago or something like that we suddenly in robotics knew how to process 3D vision effectively without having a lot of specialized hardware in computer vision algorithms running. And I think this was really one of the beginnings where robots could start to perceive and see things around them. And then came the deep learning revolution, which made vision and vision processing even more effective, and that also with 2D cameras. And then deep learning moved over to foundation models, and in between, I think Sergey can talk to us for hours most likely. Reinforcement learning went from something that people thought is not computable on a large-scale system to something which became computable. I think let Sergey complete the story. Most likely he has his own thoughts on that.
Yeah, I guess in my mind, I think one of the big things that's different now is a much deeper appreciation in the community of the importance of scale and scalable learning systems. Unlike, well, there used to be a time when even in computer vision, folks didn't entirely appreciate the importance of scale and scalable learning. But certainly in robotics, because robotic data is hard to get, robotic experiments are hard to run, and certainly in like a laboratory setting, you will be lucky if you have like one robot to work with. It kind of gets researchers into this mode of thinking where they really have to get things working at a small scale in a way that really is not just a prototype for something larger scale, but in a way that's kind of fundamentally a small scale method. And it's very tough when using machine learning to get out of like small scale mode. There's kind of this, this ravine between small scale learning and large scale learning. If you figure out small scale learning, you get something that works and you try to gradually make it bigger, oftentimes you run into trouble. And with other areas of machine learning, with vision, NLP, and so on, I think we've learned a very valuable lesson in how large-scale, simple and generic learning systems allow us to bypass much of that complexity that inundates us when we are trying to take small-scale learning and put it into the real world. So I think one of the things that's different now is that we are actually thinking about methods that will use data from many robots, methods that will transfer across different environments, across different tasks, across even different robots, and embracing that perspective of scalable learning in the context of robotics, I think is one of the things that might make this time different from the previous ones.
I think that's a great summary because now the ways we do science is fundamentally different. It's a new area of computing science where the old small-scale laboratory experiment does not hold anymore. We have to just scale study in a large scale. So following that, I think we get all from the success of these big models, LLMs particularly. What do you think it means for robotics? It's still, as a follow-up question, goes to both of you.
Well, we are in a new era of robotics. As you said, we are suddenly in the world of empirical science, we're in the world of big data, and there's, for the first time, a chance to really scale robotics to domains and also to more generalist domains, which was previously not feasible. I think the old machine learning of robotics was learn a single task and learn it well, and then move on to the next task. And now there's a possibility to learn classes of tasks or even a complete behavior set that a system needs on a daily basis. Now getting this now to performance, I think, is the really interesting challenge, which is tough. Performance, and this is the one worry I always have. If you go from, let's say, 90% performance, you want to go to 99.9% performance, your methods may fail. You may have to rethink what you're doing entirely. And the thing is, this happened in certain fields. Maybe that happens to us as well. Or maybe we find in this new data science another path how to circumvent that problem. And I don't know this yet, but this will be super exciting. Sergey?
Yeah, so one interesting lesson for me from the world of large-scale machine learning that I think is important for us to think about carefully in the context of robotics is how sometimes, instead of building up more complex systems, we should build simpler and more scalable systems. So one version of this lesson is the history of natural language processing in the late 2010s and early 2020s, where there was a lot of research in NLP around all sorts of specialized techniques, part of speech tagging, that sort of summarization, that sort of thing. So every single NLP task was sort of its own area, machine translation and so forth. And what actually ended up happening in the end is that large language models ended up subsuming a lot of that. And many of the more specialized methods that were developed for tackling individual parts of the problem in the hopes that they could then be combined into a complete natural language system ended up actually kind of being rendered obsolete by the simpler yet more scalable language models. Now, it's important not to read too much into that lesson. Like, robots are not the same as web agents, and robotics is necessarily a very integrative discipline, but I think it's very important for us as roboticists to very carefully reflect on which aspects of system building should be simplified and tackled more with large-scale learning versus which parts are kind of indispensable. And I do think that it's actually a very valid point that robotics is also quite different, that we need that level of robustness, we need that level of reliability, and it's difficult to get that out of kind of more of the same kind of learning techniques, but we should also be very thoughtful about where we add complexity versus where we emphasize simplicity and scale.
Okay, so to build those systems, I think the fossil fuel for AI, like for modern machine learning, is data. Certainly for like NLP and computer vision, we have abundance of data that's always robotics. I think that's not the case. What do you think? What type of data do we need for robotics and diversity, quality? I think I will pass this question to Peter Chen and Han Su.
Maybe I can take a step first. Thanks for having me here. I think the answer to what kinds of robot data do you need is also somewhat connected to the previous question on how do you scale actually building more generalizable models for robotics. I would say like one key difference between robotics and large language models and vision is that we need to ultimately solve a physical system. And so that means your data also need to come from physical system. I mean, you might be able to do you might be able to collect some type of proxy data through simulation, through human demonstrations, but ultimately nothing beats the kind of data that comes from robot operating in the wild and collecting data. And I would say like that has been one of the historical bottleneck in scaling robotics, because robotics was largely this effort that's isolated, fragmented in a lot of different academic labs. And the physical systems are largely built by computer science students that are typically not even hardware engineers, hardware experts. Something that has changed in this most recent wave of interest in AI and robotics is this willingness and confidence to invest in a lot of companies, like including AGI-Bot that's sponsoring the forum today. Like that really gives us much more availability of physical systems that we can run policies on, collect data. And I think that's a very structural change compared to if you look at robotics learning papers 5-10 years ago, where you see, well, very small scale experiments, very non-reproducible hardware platforms. I think we are living in a very different age of that. And so kind of my short version of the answer to the question is, you ultimately need a lot of physical robots, and you need data that come from those physical robots.
Okay, I think that I may think about autonomous driving. Maybe I think that maybe about 5 years ago, people in autonomous driving, people use some simulation and use some simulated data to train the model. Well, nowadays we know that people always use some real data to train the model. I think that similarly, currently for embodied AI, currently we sometimes use some simulated data and also use, I think that, for example, use some video data to train. Well, maybe I believe that in the future, the real data would be very, I think that we have a large amount of real data. So this is possible for us to train the data using real way. Well, I think that still bottleneck is about how to collect data. I think that low cost and maybe much more efficient. Yeah, currently I think that maybe the telecooperation, maybe the efficiency is not I think that's satisfactory. So I think from my perspective, actually, I like for example, the robot-free data collection above that. For example, the UMI data collection, such kind of data exercise. In this, it means that we can scale the data collection, make it scalable, much more efficient. So I think although the robot-free data collection method is not very, I think that maybe reliable because you have somewhat a gap between the robot and but I believe that maybe in the near future it will be one of the possible way for the data collection. Well, anyway, I think that as far maybe we may have a large amount of real robot, it means that we can have a large amount of data set. Then how to use them? I think that maybe for lifelong learning, maybe it means that we have a closed loop of the data reuse stack set. This will be maybe in the future of data. Okay.
So I think we talk about the data, and then I know, Sergey, you recently actually wrote a little blog post about the data part. It's called Spokes of AGI. I really like that blog, but as a panel host, I have to stay neutral. So I guess my question is really, how should we get the data? Like, what do you think about the real data versus simulators versus some other ways of getting data? I think I will pass this question to Sergey and Martin. Maybe Sergey, you want to take a first leap?
Sure, yeah. So I think Peter actually said it really well, that real data is very important, and I think that maybe to add to that a little bit, I think if we look at other domains, across the board, what made machine learning work in areas like computer vision and NLP is being able to effectively leverage very large real-world data sets. Now, that doesn't mean that that's the only data that we should be using. What it means to me is that the way to get to a generally capable robotic foundation model is to get large robotic data sets and use them to learn a general understanding of physical interaction and the physical world. And I think once we have that, a model that has a good understanding of physical interaction in the real world will actually be more able to absorb other sources of data. As a person, if you watch a cartoon or play a video game, you understand the abstract kind of world, even though its graphics don't necessarily quite reflect reality, because you're very grounded in the physical world already. So I think if we can build up that understanding of physical interactions from real physical data, we'll be in a much better place not only to make a lot of progress in robotics, but also to then absorb other data sources. So I think that actually it's not that simulation is the thing that will bootstrap robotics. It might actually be the other way around, that large-scale real-world data sets will bootstrap the ability of the robot to understand all sorts of other types of data as well.
Okay, so I'll discuss from a different kind of perspective. So a lot of times people are arguing about the cost of acquiring certain type of data, right? Saying one way of getting data is cheaper or more expensive than the other way around. But remember, each kind of data collection process has its own cost associated with such a method. For example, like a human labor cost is one aspect, and the other way, we have also the storage cost, and the amount of data is also associated with the amount of compute we need to train the model to consume the data. So sometimes certain way is cheaper to collect, but it's more expensive to store and consume. So that's one way. And also, I don't think like in the long run, if we take a step back, collecting data spend millions of dollars, hundreds of millions of dollars, or even billions of dollars is a unaffordable thing, given that, I don't know if you guys noticed recently, Meta's superintelligence lab, they hired one researcher for 1.2 billion or something, right? So the amount of data, money can easily get us hundreds of millions of trajectories. If that's the passcode we can unlock the AGI, I don't think any tech giants or countries will hesitate to spend that amount of money. And eventually, I think it comes back to not the way of getting the data, but it's how to effectively get the most representative data from different kind of application domains and industries. So I very much agree with Stefan's early presentation that we need tons of ASI systems work in the real world, work in the field, to get us the most valuable and sometimes even corner cases, failure cases, to help us effectively iterate our system. So I think by the time we have millions of robots deployed in the real world, our trouble is never how to get the data inexpensively and choose the way we get data. Our trouble will be how can we sort out the most useful data out of the billions, trillions of trajectories, because we cannot afford to store them or to consume them. So in the long run, I think we will be more worried about that. Yeah.
I think I actually agree. Also, both of you said, and also Peter mentioned, like the embodied agent should be situated in the physical world. It's just like if we look at LLMs, what is LLM learning? Like we have all these human thought or human whatever brain activities, human thought typed into internet, or you talk to the podcast. It's really imitating that, but it does not, let's say, reverse the process that actually generates the thoughts. That's how we figure out how the brain works. But if we want to build a machine that could actually sense, act, reason, act in the physical world like a human, it has to actually be placed in the real world, interacting with the environment, generating a lot of interaction data. And then by the end of the day, we have those all sorts of like heterogeneous data. Our trouble is not how much we have, it's just really how we deal with it. So I think we have also talked about a lot of like, Stefan, you mentioned like, at the moment, we really need the performance, we need the specialist aspect. And Sergey, you mentioned that we really should just put generalization as a first-class citizen and go from there. I'm curious about two of your views on the generalist versus specialist comparison.
Sergey, do you want to start? I started twice before.
Sure. So I think it's a very complex question because clearly we do need robots that are actually useful for particular application domains, and being useful in an application domain means that you are at least somewhat specialized to that domain. But I think a lot of what holds back robotics from being applicable in open world settings, in your home, in an office, in a hospital, really has to do with its ability to handle a wide variety of unexpected situations. And that means having generalist capabilities. Essentially, being a generalist gives you a kind of robustness because it allows you to handle all sorts of strange situations in a reasonable manner, including situations where you simply made a mistake and failed at the job that you were trying to do and need to somehow correct that mistake. And I think that overcoming that bar where robots have the common sense to act reasonably in real-world settings is a really big deal, because at that point we can start deploying robots in real-world settings where they can gain experience and become more and more specialized. So it would unlock the path to specialization through experience. So because of that, I think generalist skills are really, really important because it's one of the big obstacles in the way of robustness in open world environments.
Yeah, let me add to this a little bit. And again, I think that the message is really, what do you want? Where do you want to go? How quickly would you like to have a robot actually doing something? How quickly would you like to have a robot doing something which helps someone to make someone really happy? And these are different paths. The generalist is clearly what we all would love to have. And also, if you go more in industry task, in industry there's increasingly more something which is called high mix, low volume production. That means things change a lot. And when things change a lot, people don't want to retrain a model for half an hour, an hour. Well, half an hour might be okay. If it's hours or days, then they will not be so happy about this. So then one-shot generalization, and then getting increasingly more into foundation models. How do you get to one-shot generalization methods? And all of these techniques, I think, whatever path you go, hopefully it creates data. And this data can be used for the next robot to get better and basically become more general. And again, these are just different pathways, what you would like to emphasize, whether you would like to get something to a customer in the next 2 years, or whether you have another few more years' time before this happens. I think it's all very valid. It's all different approaches. And indeed, I think we should all use different approaches. It would be terrible if we had just one monolithic approach.
Okay, great. Now I want to actually switch the topic a little bit. I think there's always a gap between academia and the industry. In robotics, this gap, in my opinion, is much more pronounced because usually in an academia paper in the setting, you do something, you record a video, you upload to YouTube, and then you move on. You never care about the things that actually happens after that. So my question to Peter and Stefan, because both of you actually have navigated between academia and the industry, is that how do you see this, and what would you think, what do we need to do actually to shorten the gap?
Okay, I can go first. The first one is you cannot move on. Like if you deploy a policy in the real world, like you're stuck with it because like robots are supposed to work 24/7. So if your policy breaks somehow, you need to go back and fix that. Like that's very different from uploading to YouTube and just forget about it. I mean, there's something that's very annoying about it because like you're actually accountable for what your policy, like how good your models are. But there's also something very appealing about it, right? Like you actually get to experience how your model would fail in all kinds of long-tail cases. That informs how you should improve the generalizability, robustness of your system. Then coming back to the more general question of like how should academic research and industry research work together for robotics, I think we should try to shrink the gap as much as possible, like, because this is not a field where there are already established techniques, recipes that you can just apply and build products from it. There's still a ton of frontier research that needs to be done. And that's still something that I would say the minds and talents that are being developed in academia are still the best place to do a lot of those frontier research. But at the same time, like there is a domain gap problems, right? Like a lot of academic researchers don't really know what are the practical problems that we need to solve. So I think folks in the industry have an obligation to bring some of those problems, some of those motivations back to academic research. And it's my perception that a lot of the academic researchers have the incentive to also work on problems that are closer to the real world. So I think the gap historically exists, but I hope it will shrink over time in the next couple years.
Yeah, I think these are super valid points. Let me add just a little bit to that. In some sense, we are asking also the question, how do you go from a prototype to something which really, really works? And, well, fine, you can put the work in with the right people who are interested in doing this technology transfer, which is fantastic if you can do this. But there's also a possibility to choose the problem settings in which you would like to work a little bit such that it's more tolerant towards an initially not so well-performing system. Since not everything is car industry where you have to be 99.999% perfect in order to make things work. There's other things, and I think one nice example was actually the trash sorting at Everyday Robots from Google some years ago, which was much more tolerant to failures because trash sorting just needed to be like above 90% or something correct. So you didn't have to be perfect. And there's domains where you don't have to be perfect, where you can have a human still standing there, which supervises a couple of robots, and then slowly move your way to perfection over time, since it may just take some time and potentially take more data in the end. So I think that this category is also super helpful. Let's not aim for every task in the world to be solved by a robot. Choose wisely.
Sure. We talk a lot about robotics, right? But I think robotics is too broad of a topic. Like you can call autonomous car as a robot, and you can call humanoid as a robot. And also there are different problems for us to solve. If we're going to name it, I think the three major things we care about is navigation, locomotion, manipulation, right? What do you think? What do you think out of these three is the biggest significant challenge for us right now, and how should we solve it? So I would like to pass this question to Sergey and Stefan.
Sergey.
I can start. Yeah, it's manipulation because it's the hardest.
What about the other two?
They're easier. So the reason is this, that for manipulation, it combines the challenges of everything else, because manipulation requires you to understand a very diverse and complex world and to interact with it physically. For navigation, we need to understand a complex world, but we typically have relatively simple physical interaction with it. And for locomotion, we have physical interaction, but the world is a bit simpler because the only thing we're really applying forces to is the robot itself. Obviously, we can complicate each of those settings a little bit, but manipulation is the one that really brings out the confluence of all of the hardest challenges. And I suspect that if we can have a solution for robotic manipulation that is general and broadly applicable, whatever ideas we come up with to do that will also give us a really good head start on the other problems also. And that's not to say that nobody should work on navigation or locomotion. I think they're great problems to work on, and isolating a problem domain that is not as complex, that doesn't have as many difficult factors combined together, can allow us to make a lot of progress by tackling a challenge in isolation. But manipulation is the hard one that brings all the challenges together.
Yeah, maybe just adding to that, this is absolutely correct, everything. The fun thing is everything comes together sooner or later anyway. So we've done manipulation on a fixed base arm. We know how to do this to some extent. Still, we're not nowhere good enough to do this well. I think locomotion in isolation by now has become fairly robust and amazingly good, which used to be a problem like 10, 20 years ago. And navigation by itself, well, SLAM has been around forever after. SLAM in isolation, we know how to do. Doing navigation with a lot of sensory input in a very uncertain world, what I think autonomous cars are having to solve, becomes significantly harder. But now you can put this all together and just put it on a humanoid. So now you have a locomoting mobile platform which wobbles around like crazy when you move your arms, and then you have to do manipulation and you have the entire misery altogether. But manipulation is still the one which is the least mature. I think this is what it is, and we have to get better at this.
Can I push back on the two guests? I think there needs to be some spiciness to make this kind of a discussion more interesting. Like, while I agree with the framing that manipulation is the least solved among these three domains, like, I still feel like it's not quite correct to call manipulation kind of like the only problem wolves. I mean, I know that's not your word, but kind of exaggerating a little bit. And here's the reason why. Like, I mean, solutions, navigation share the same foundation with any of the methodologies we're working on manipulation, right? Like doing SLAM to solve navigation, and then some local sim to real policy to solve locomotion, then doing something different to solve manipulation, it's just not building up a common sense understanding of the physical world that we are really after. And so in some sense, like, yes, like we can say there are other clutches that we can rely on for navigation and manipulation, for navigation and locomotion. I do think there is a more fundamental common sense understanding problem that we are after, like, which is kind of like what we want to signal through this word foundation model that we're not quite solving yet.
Fully agree. Speaking of that, just follow what you said, I think people right now believe different ways of solving robotics. Some says simulation, some says we should collect 1 billion real-world data trajectory, some believe in water models. This is a question for everyone. Everyone can just speak whenever you feel the moment. What would you think will be the next frontiers in next 3 to 5 years?
I'm happy to start with a thought, at least. And one thing which I would love to get back to, which is actually a very old topic, is continual learning. We've had continual learning with smaller machine learning models. Adaptive control is when you can prove that it actually works. And how do we put this in the context of large models and big scale models? None of you ever stops learning, at least I hope. In our robots, most of the time, learn something and then they execute and evaluate and then they start learning again. And we are still worried about how to add data all the time without ruining the system, without going out of control and doing something terrible. I think this topic would be fantastic, and that would accelerate actually the way we can build up big models and better machine learning models.
Okay, actually I agree. I think that maybe the next front would be learning maybe learning from the feedback, continuous learning from the feedback. Currently, I think that the learning strategy about that, okay, we have hardware and we train the policy like that. Well, I think that in the future, we would have a policy, well, by maybe continuously improve the policy by interacting with the environment while learning from the feedback. Currently, I think that maybe for reinforcement learning, the sampling efficiency is not very desirable. So how to make best use of the feedback would be the next, I think that's frontier. Okay.
Maybe I can add on. So talking about the frontiers in the next few years, I think we still haven't fundamentally verified all of our hypotheses of scaling laws in the embodied intelligence field. The problem is still we don't have enough amount of data that's comparable to the language domain. And I think in the next few years, we probably still need to stick with that extrapolation and see where we hit the plateaus. And also, different from the language domain, we are working with, there we are working with discretized symbolic tokens or representations, but the real world, continuous world is more complex, and we have all kinds of interactions with the world, and this is something that might significantly differ from our experience in the language domain, right? So I think all of these are real frontiers we want to conquer, yeah.
I think this is maybe a bit similar to what the other panelists also said, but I think that increasingly the most important problem will become how to use data from robots that is autonomously collected and maybe not that good. And the reason for it is that right now we are kind of in this bootstrap stage in robotics. We're figuring out the technologies that will get robots kind of out of the lab and into real world settings. And if we are successful in that, then there will be robots in real world settings. And once something is useful, people tend to make a lot of it. We can look at cars, even autonomous or partially autonomous cars. There are many of them on the road now. When we have a future where there are hundreds of thousands or maybe millions of robots out there, then of course the most important thing for us will be to figure out how to make them better using the kind of experience that they naturally collect, which will probably not be as good as the high quality teleoperation data, and we won't be able to control it as tightly as we control simulators, but that will be the source of a lot of additional knowledge for these systems, and we'll have to figure out how to use it.
Okay, I think I will ask the last question because we have a time constraint today. A lot of people sitting here are students, and also a lot of researchers actually get into the field in the past 2 years. What advice do you have for students and for young researchers, junior researchers just getting into the field?
Maybe I can start, and also answering the last question on what the frontiers I'm most excited about. I'm most excited about getting more robots that are doing useful tasks, because when we talk about the data problem, we don't have an internet of data to mine, but we have a different opportunity. We can build the robotics pre-training data that are actually a lot more useful from the get-go, right? If you think about what's the challenge of getting Common Crawl into large language model pre-training data, it's filtering out a lot of noise and junk that exists on the internet. But if if the folks in this room, students, researchers getting into the field now or have been in the field, try to solve a large set of useful problems with robotics, then we get very useful, interesting data, and we have an opportunity to build up this corpus that is very valuable from the get-go. You don't need to filter down from a bunch of junk.
Okay, maybe Stefan can say a few words.
Yeah, happy. So very, very short. Fine, we try to get into physical AI. So my recommendation is learn about physics, learn about AI and machine learning, and I think you need to learn about big data science as well, since that now all belongs together, and in order to get to this physical AI, I think we need people who have knowledge in all of these disciplines.
Sergey, do you have advice for students?
Yeah, so I think one bit of advice that I think is important to keep in mind when selecting what to work on is to really think carefully about whether it's a problem that is merely addressing a practical convenience or whether it's something that might have the chance to address something truly fundamental. And I think in robotics especially, because we have to be at least somewhat practical, we have a tendency to fall prey to like somewhat smaller thinking. Like think about how to address a particular practical challenge that you get into when you only have one robot in your lab, or when data is expensive, or when compute is expensive, and so on. And I think it's really important when selecting what to work on to really step back and ask, like, is this actually just making things cheaper or more convenient, or is it something fundamental? And, you know, there are some examples of works that when they were done, people sort of didn't think it was very practical, but in the long run, at scale, with, you know, a lot more resources, it turned out to be very important. One example of this was Paul Cristiano's work on deep reinforcement learning from human preferences. When this work was done, you know, he tested it at small scale on getting a little simulated hopper to make a backflip. And it seemed like it was taking deep RL, which was already expensive and impractical, and making it even less practical by requiring a person in the loop to provide preferences. But of course, years later, this turned out to be the bedrock of RL from human feedback, which we use for fine-tuning LLMs all the time now. So it's very important to kind of get past.
Okay. 好，谢谢 ，Thank you so much for the wonderful sharing。在这里要再一次感谢我们所有舞台上给我们